Alright, so here's the problem. This is problem 1-34. Again, this is statics and mechanics sort of review. Goes a little bit farther in the depths as far as strengths goes. So the question is, let me cover all this crap up. These are homework problems, so I've already done them and I'm just going over them for a test here. So hopefully this will be able to help you guys out. Alright, so 1-34, the buildup of the shaft consists of a pipe, AB, and solid rod, BC, as shown here. The pipe has an inner diameter of 20 millimeters and an outer diameter of 28 millimeters. The rod has a diameter of 12 millimeters. Determine the average normal stress at points D and E and represent the stress on a volume element located at each of these points. Alright, so I drew a picture here. Kind of representing the rod and pipe here, and the diameters. This is the rod, and this is the pipe. Alright, so we're trying to find the average normal stress at point D, which is actually here, and point E. Alright. So, let's take a moment and look at what normal stress is. So, normal stress is force perpendicular to the cross-sectional area. So, if I were to draw a picture here, we're going to have a force coming out, and this is the cross-sectional area that we're looking for in the pipe. Alright, so the first thing we're going to do, we're going to draw a free body diagram. Alright. And to do that, let's cut the member D, and we'll say the force acting at point A, X0, see here, so we have a shear, a normal force, and a moment. Okay, so we have a shear, moment of reaction, Fn. These are both going to be equal to 0 because we only have forces acting in the x direction. If we had forces acting in the y direction here, we would have a shear and a moment. But for now, we're not going to deal with that in this problem. So, since this is our free body diagram, let's sum up the forces. We'll do support reactions. So that would be this support reactions. And this is just to determine the forces that are we know, or the member we know is in equilibrium. So we're going to determine this is 4 kilonewtons, Fn. So Fn, we'll do some of the forces in the x equal to 0. It's going to be, we'll call that positive. Make sure to label this positive here. Otherwise, you don't know which way is up or down or left, right. You basically just get lost, and you'll make a mistake. So we know 4 kilonewtons is positive minus Fn. Fn is equal to 4 kilonewtons. Write that in there. Alright. So now we need to determine the area of the cross section. So see area. And our area is going to be, see here, pi over 4. Alright. So in order to solve this, we're going to plug in our outer and inner here. So we have pi over 4 times 28 squared minus 20 millimeters squared. And I'm just getting this from these numbers here. And that is equal to our area. And you plug these numbers into the calculator here. So we have 28 squared minus 20 squared equals divided by 4 times pi. It's 301.59. And that's going to be millimeters squared. Alright. So to find the normal stress, we're just going to divide here 4 kilonewtons, which is 4 times 10 to the 3 newtons divided by 1.59 millimeters squared. And that is equal to 13.3 megapascals. Alright, and notice here we have megapascals, and that just has to do with our force here. We have mega, let's see here, mega equals 10 to the 6th power, because we have goes kilo, mega, what's the other one? Well, anyways, kilos 10 to 3, 10 to the 6, and milli equals 10 to the negative 3, and when we square 10 to the negative 3, we're going to get 10 to the negative 6, and that's going to give us 10 to the negative 6 millimeters. And when we put this underneath our newtons, so we'll have newtons per 10 to the negative 6 millimeters, and that is going to give us 10 to the 6 newtons per millimeter, which is our definition of megapascal. So that kind of explains where this mega comes from. Alright, and to do a let's see here, the problem is asking for representative. It says represent stress on a volume element located at each of these points. So to do that, we'll just say, we'll pretend that point D here is an infinitesimally small point, and just make this our cross section here, and this is going to be distance x, and just pretend just x is really small. Now we're going to represent the stress acting on this cross section. It's kind of a sloppy picture, but you get the point. So what is our stress? This is our stress. Which way is the stress acting? Well, the stress is compressive, right? So let's draw the member in compression, and we say 13.3 megapascals, and the reaction is 13.3 megapascals. Alright, and notice that the member is in compression. Once again, I think that's kind of what this problem is trying to get at. Our stress, our normal stress, is a vector And so it's trying to show you that the stress is compressing the member, and eventually the member will break. Actually, when they put them into a machine, and the machine just puts a large amount of force on the member, and the member basically looks like Santa Claus after a few too many beers there. So the member just starts bulging out at the ends, and eventually it'll break. So I'm gonna leave out this second part of the problem. I want you to practice doing that just for time's sake here. But it's essentially the same thing. You go through, you draw your free body diagram, you work out your support reactions, find the force normal here, and in this case it's going to be 8 kilonewtons. You can see that by looking at it, and then divide your area. So that's pretty much it.